let's extend the second law to open systems. And so what we're looking at now is the schematic of the open system that we discussed previously back in chapter 3, right? Where we know that the system, which is some sort of liquid or fluid going into a tank, the inlet stream has some sort of mass flow rate, temperature, pressure, and energy associated with it. And the outlet stream also has some mass, temperature, pressure, and energy associated with it well. But now that we've brought up the concept of entropy, what we also need to remember is that the inlet, outlet, and the system itself all have some sort of entropy associated with them. Okay? And so our entropy balance needs to account for this incoming and outgoing entropy as well. And so in an open system, the entropy balance, or SB, needs to account for entropies of the incoming and outgoing streams. Okay? And so what we could do is we could take the rate form of the energy balance and we can modify it like so. And so that's essentially what the open system entropy balance is going to be. Right? And so for the open system, what we write is ds dt is equal to a summation term that accounts for the incoming and outgoing entropies of the incoming and outgoing streams, where once again alpha here is positive for inlets and then negative for outlets. Okay? So we have that, and then we add on the other parts of the entropy balance. So I'll call this M Q dot J over Tj plus our Sgen. Okay? And we have to remember that Sgen, its value is going to depend on what type of process we're dealing with. So it could be greater than 0 for an irreversible process. It could be equal to 0 for a reversible process. And it will be less than 0 only if the process we're discussing is not physically possible.